Hey everyone, welcome to the Explainer. I am absolutely thrilled you're here with us. If you're looking to really wrap your head around the mechanics behind the massive, real-time systems powering our digital world today, well, you're in exactly the right place. Today, we're diving straight into Chapter 11 of our source material, focusing entirely on stream processing. We're going to explore a massive paradigm shift in system architecture, specifically how modern data systems handle never-ending, continuous streams of information. We'll unpack the architecture directly from the source to see how it shapes the apps we literally rely on every single day, and why this shift is just absolutely crucial for modern engineering teams.
So, to kick things off, let me ask you this. What actually happens when your data never stops arriving? In the old days of data engineering, we leaned heavily on end-of-day batches. You'd basically sit around and wait until midnight to process all the sales or clicks from the last 24 hours. But let's be real, today's users are impatient, and modern businesses completely run on immediacy. Whether it's a fraud detection system catching a shady transaction, algorithms running high-speed financial trades, or honestly, just refreshing your social media timeline, we need instant reactions. Your system literally cannot wait until midnight to tell a user someone stole their credit card. So, how do we process data that simply has no end?
Okay, here's our game plan for today. We're going to cover the never-ending data stream, transient versus durable brokers, why databases are actually streams, the Star Wars time problem, and finally, achieving exactly once fault tolerance. Let's jump right in. Starting with Section 1, the never-ending data stream, let's quickly define the core problem by comparing batch and stream processing. There is a really stark contrast between these two paradigms. Batch processing operates on bounded data. That means the data has a fixed, known size, like, say, a specific log file that was generated yesterday. Because it actually has a defined beginning and end, a batch job will eventually complete. You run it, it finishes, you get your result. Simple. But stream processing, that deals with unbounded data. It's a never-ending flow. You're incrementally processing data in near real time, basically right after it happens. And because the input literally never stops, a stream processing job is never truly finished. It just runs constantly, reacting as the world changes minute by minute, second by second. Now, in this unbounded world, our fundamental building block isn't a static file or a database table. It's an event. An event is just a small, self-contained, immutable object that records the details of something that happened at a specific point in time. Think of a credit card swipe, a temperature reading from an IoT sensor, or a user clicking a link. And here is the absolutely crucial part. Events are immutable. Once it happens, you cannot unhappen it. A producer generates this event exactly once, and then multiple consumers can process it downstream. This concept of immutability is the bedrock of building reliable real-time systems. Moving right along to Section 2, let's talk about transient versus durable brokers and how we move these events around. So, to transport these millions of events from producers to consumers, we use message brokers. Now, traditional brokers, like the ones using AMQP or JMS standards, they're built with a transient messaging mindset. In those older systems, as soon as a consumer successfully processes and acknowledges a message, the broker just deletes it. Poof, it's gone forever. But modern log-based brokers, like Apache Kafka, take a totally different approach. Instead of deleting messages the second they're delivered, they durably append them to a log on a disk. It operates a lot like a database replication log, which means the data actually sticks around long after it's been read. And having a durable log gives you some massive architectural advantages. Because reading a message doesn't destroy it, you get to easily implement multi-consumer fan-out. This means several totally independent systems, say a billing service and an analytics dashboard, can read the exact same stream of data without stepping on each other's toes. Plus, it drastically prevents data loss if a consumer happens to crash. But honestly, the coolest part, it lets you replay old messages. Since the data is just sitting there securely on disk, you can spin up a brand new consumer, point it to an older offset in the log, and reprocess yesterday's data to test some new code. You're effectively time traveling to debug your system. Which beautifully sets up our next massive paradigm shift in Section 3. Databases are actually streams. I want to share a quote from software engineer Pat Helland. He says, "The truth is the log. The database is a cache of a subset of the log." Just kind of let that sink in for a second. When you update a row in a traditional database, under the hood, that change is being written to an append-only log. So the table you end up querying, it's really just a materialized view. It's simply the latest, cached state of that never-ending log of continuous changes. When you think about it, mutable state and an append-only log of immutable events are really just two sides of the exact same coin. And we can actually put this philosophy into practice using something called change data capture, or CDC. CDC basically lets us observe all the writes happening in a static database, extract those changes into a continuous log-based stream, and then apply those changes to derived systems in the exact same order. This is exactly how modern architectures keep a complex search index or an in-memory cache perfectly in sync with a primary database. Through CDC, your static database is transformed into a flowing stream of events that your entire infrastructure can listen to and react to. Now, an even deeper application of this whole idea is event sourcing. Instead of extracting logs from a database after the fact, your application logic is explicitly built from day one to record immutable events that capture user intent. So rather than overwriting a user's address in a database table, you just append a user-moved event to the log. The current state of the user's profile is then derived simply by replaying that log. If a bug creeps in or something goes entirely wrong, well, the fact remains that those original events still occurred. This gives you an absolute, fully auditable history of your system that literally can never be accidentally overwritten. Now, processing these event streams sounds super elegant in theory, right? But in the real world, things get messy fast. That brings us to Section 4, the Star Wars time problem. So think about the Star Wars movie releases. Episode 4 came out way back in 1977, but Episode 1 didn't arrive until 1999. If you watch the movies in the exact order they were released in theaters, the order you process them in completely mismatches the actual internal narrative timeline of the story. Now, as humans, we can easily piece that narrative back together in our heads, but for a stream processing system that's trying to aggregate data, that discontinuity is a massive headache. And this analogy perfectly highlights a really tricky distinction in stream processing: event time versus processing time. Event time is the exact moment the event actually occurred out in the real world, so the narrative episode number in Star Wars. Processing time is when the event finally arrives at the server and actually gets processed, like the actual release year of the movie. Because of unpredictable network delays, maybe a mobile device going offline in a tunnel or a server restarting, events very often arrive completely out of order or severely delayed. A robust stream processor absolutely has to analyze data based on when it actually happened, not just when it happened to show up at the data center. To handle all this chaos, stream processors group these time-stamped events into time windows. Let's break them down quickly. Tumbling windows chunk time into fixed, non-overlapping periods, like every exact minute. Hopping windows are also fixed, but they overlap, say a 5-minute window that advances every 1 minute. Then you have sliding windows, which group events that happen within a certain proximity to each other, completely ignoring fixed boundaries. And finally, session windows. These group bursts of user activity together, and they only end when the user actually goes idle for a specific amount of time. Choosing the right window type is basically make or break for getting accurate analytics when your data is arriving out of order. All right, we've tackled the complexities of time. But what about inevitable hardware crashes? That brings us to our final topic, Section 5, achieving exactly once fault tolerance. In a traditional batch process, if a machine crashes, whatever, you just restart the job from scratch. But in a never-ending stream that's been running continuously for months, you obviously can't just start over from the very beginning. To solve this, frameworks use a few really clever techniques. One popular method is microbatching, where you break the continuous stream into tiny 1-second chunks and treat each little chunk like a miniature batch process. Another absolutely critical technique is checkpointing. The framework regularly saves the consumer's offset, its exact place in that durable log we talked about, along with the current state of any time windows. If a crash happens, the system just discards any partial outputs, restarts from the last valid checkpoint, and smoothly replays the unacknowledged messages. But hold on, replaying messages creates a brand new problem. What if an event side effect, like, say, writing a new bank balance to a database, happens twice? This is where idempotence comes in as your secret weapon. An idempotent operation is one that produces the exact same result, whether it's executed once or 1,000 times. By combining strict log offsets with idempotent writes, modern stream processors ensure that even if a message gets redelivered after a nasty crash, it's effectively processed exactly once. Your system's final state remains perfectly accurate. Well, we've covered a whole lot of ground today, from unbounded events and durable Kafka logs to handling the chaos of event time and finally, recovering gracefully from system failures. I want to leave you with one lingering question to chew on. If every database is really just a stream waiting to happen, what does that mean for the future of your own application's architecture?
The shift from static, resting data to continuous flowing streams changes absolutely everything about how we design reliable, scalable systems. Thank you so much for joining me on this deep dive in the Explainer. Keep learning, keep building, and I will see you next time.